Hello everyone, we are Group 11. In this project, we compare the performance of an UNet and the segment anything model on COVID-19 CT lesion segmentation. Our goal is to see how a CNN baseline compares to a new prompt-based foundation model. And before methods, let's define what is the medical image segmentation. It means selecting exact pixels that belongs to a region of interest. For example, drawing the boundary of a lesion. And this is important because the radiologist needs to check hundreds of slices and the manual drawing is slow and subjective. So the automatic segmentation can reduce the workload. It can also make measurement more reproducible and more stable. And over the years, segmentation methods evolved in several stages. The early approaches were classical image processing, like the thresholding or the region growing. But these methods failed in some complicated cases. And then the CNN-based models, such as the UNet, became the dominant baseline because the encoder-decoder structure captures both the context and the detail. And more recently, transformer-based segmentation appears to model longer range dependencies. And the newest line of the work is prompt-based model like SAM, where the segmentation can be guided at inference time using points or boxes instead of retraining the whole model. And we use a COVID-19 CT scan lesion segmentation dataset from the cargo. It is structured by merging the lesion-labeled CT slices from 3 publicly available datasets and resulting in over 2,700 image mask pairs. And each sample contains of the 512 the grayscale CT image and corresponding lesion masks. And the UNet is based on the UNet. And the UNet is it uses an encoder to compress information and a decoder to recover spatial details. And the encoder applies the repeated or 3x3 convolutions followed by a 2x2 max pooling. And the decoder upsamples using 2x2 up convolutions, and then it also uses skip connections to bring back some high resolution features from the encoder. And this is why UNet works well in the medical segmentation, because it preserves the fine boundaries that really matter for the lesion shape. And the special thing of the UNet is that it self-configures to any new dataset. When we give it a new task, it builds a dataset fingerprint. And it checks the image spacing, image size, intensity, foreground ratio, and so on. And then the heuristic rules set many hyper parameters automatically, like the patch size or the batch size and the network depth, and also some augmentation. Along with that, there are some fixed parameters like they never change, like the core architecture. And then the UNet runs up to 3 setups. And does the 5-fold cross-validation and picks the best model and post-processing by itself. And for some public datasets, the UNet even provides the pre-trained weights. For example, the text 115, and we will use it later. So in this project, we did 2 UNet experiments. First, we downloaded the text 115 pre-trained weights and directly ran the inference as baseline. And second, we also take a fine-tuning run. We took 90% of the dataset as train and validation and trained the UNet, and then we evaluated on the remaining 10%. The pipeline includes converting the data format and placing them into the NUNet directory structure and setting the environment variables and calling the NUNet predict. Here is an example output. The yellow region is the ground truth and the green region is our prediction. Overall, the shapes look similar, but there are still some mismatches, like some regions are segmented and slightly shaped. This leads to our next step. Can a prompt-based model like SAM do better without training?
So in this project, besides the NUNet model, we also explore the use of segment anything model in our COVID lesion segmentation task. The SAM model is a promptable foundation model used for image segmentation. It is pre-trained a very large data set of natural images. It has this three main components: an image encoder, a prompt encoder, and a mask decoder. The image encoder is the pre-trained visual transformer that can turn an input image to an image embedding vector. The prompt encoder can encode prompts given by the users, which can be points, bounding boxes, and texts. It uses like position encoding and clip encoder to encode the prompts. The model can also take rudimentary masks as prompts, which are embedded using a convoluted neural network. And eventually, the mask decoder, which is a modified decoder block of the transformer model, will take the image embedding vectors, will take the prompts embedding vectors, and eventually output a list of masks along with their confidence score. So in the experiment, instead of prompting the model manually, we used this automatic max generation pipeline from the transformer library. The pipeline will automatically generate a grid of 1,024 points evenly across the image, and will then sequentially feed mini batches of those points to the model as input prompts. It will generate a list of raw masks, and then we'll do the post processing. It will like remove overlapping masks, will remove bad quality masks based on IOU score and stability score thresholds. It will eventually retain a list of all the high quality relevant masks as output. So this slide shows the final output of the pipeline, which is a list of NumPy arrays. Each NumPy array corresponds to a final mask post-processed by the pipeline. So because the COVID long lesions are often scattered and non-contiguous, and also because the fact that some automatic mask generation pipeline only generate separate masks, so we have to define this like combining mask function, in which we use the like IOU score as a threshold to kind of identify and retain the masks that really correspond to the true lesions in the ground truth mask, like in combining them into a single final mask for further evaluation. So this is the output. We got like a final combined mask from a list of outputted masks by the pipeline. And this slide shows the comparison between the ground truth mask and the predicted mask. And we can see that we also explore the use of a much denser grid of points. We double the points on each side to get another predicted mask, but it doesn't show like much of a improvement. Because we set the IOU threshold to be 0.1, so we can see that we missed some small lesion compared to the ground truth mask. So in this project, we used three different evaluation metrics to evaluate the performance of our segmentation performance of our model. The first one is stat similarity coefficient, which quantifies the overlap between a predicted region and the corresponding ground truth region It is defined as the two times the intersection between the two regions divided by the sum of two regions. The second one is the intersection over union index, which is another measure of such similarity, and it's defined as the intersection between the two regions divided by the union of two regions. The third one is the 95 percentile Hausdorff distance, which measures the spatial discrepancy between the boundaries of the two regions. So this slide shows the final comparison of segmentation performance between the N-UNet model and the segment anything models evaluated by the three metrics. We can see clearly that the UNet model outperforms the SAM model in all the three metrics. And after the fine-tuning, the NUNet model performs much better. And for SAM model, we didn't fine-tune the model, but we explored the use of a much denser grid of points. We double the points on each side. But it didn't provide like you only provide like a very minimum improvement in the performance. Uh, so in conclusion, in the project, we explored the use of UNet and segment anything model for segmenting COVID-19 lung lesions on CT images. The NUNet model was fine-tuned on our dataset, where the SAM model was evaluated in a zero-shot setting using its automatic mask generation pipeline with different grid point configurations. The segment performance was assessed using three different evaluation metrics. What we find is that the fine-tuned NUM model consistently outperformed SAM model across all metrics. Well, SAM model's zero-shot generalization is impressive, but it struggled to detect small or diffuse lesions accurately without fine-tuning, without task-specific fine-tuning. And increasing the number of grid points inputs yielded only marginal improvement, highlighting that the fine-tuning is crucial for accurate medical image segmentation. So for future work, we can fine-tune the SAM model on our data to evaluate its full potential for medical image segmentation. We can also experiment with different IOU thresholds or integrate other metrics such as dissimilarity coefficient when we're merging the masks to better retain true lesion regions. So with that, we conclude our presentation. And thank you very much for your listening.